Hi folks! This is our second video on notation, and today I'm going to be talking about resonance. I want to begin by talking about molecular orbital theory for cases where we have pi bonds. Let's imagine this 3-carbon molecule where I have a pi bond. Here I've labeled my 3 carbons, and notice that my pi bond is between carbons 1 and 2. Our pi bond contains 2 pi electrons, and because it only is existing here between carbons 1 and 2, we would say that it is localized between these 2 carbons, numbers 1 and 2. In order to form our molecular orbitals for this pi bond between carbons 1 and 2, we're going to take 2 p atomic orbitals, one each from carbon 1 and carbon 2, and we're going to combine them together. Here's the beginning of my pi molecular orbital diagram. And because I'm trying to form a pi bond here, I'm considering a p orbital from each carbon. When I bring these 2 p orbitals side on in a constructive way, I end up with overlapping sides of p orbitals. Notice that my phasing matches on the top and on the bottom of these 2 p orbitals. This looks like our pi bond that we saw in hybridization. But in molecular orbital theory, if we mixed 2 orbitals in, we need to get 2 out. And so we also need to consider the destructive combination of these 2 p orbitals. What this would look like is having p orbitals side to side, but instead of having the lobes on the top and the bottom matched, now they are mismatched. Through the middle of the molecule is what's known as a node, which is where there is no electron density present, and I get this when I have a mathematical sign change. For example, from unshaded to shaded. Notice that my 2 electrons reside in the lower energy molecular orbital. I call this lower energy orbital my bonding molecular orbital, and I call the higher energy one, that's empty in this case, my anti-bonding molecular orbital. Now let's consider this closely related molecule, where I still have 3 carbons, but now the one on the right has a positive charge. I'll use my same 1, 2, 3 carbon naming system as before. So let's think about the carbon on the right, which has a positive charge. Carbon 3, the one with the positive charge, has 3 bonds, 1 to carbon 2, and 2 to hydrogens that aren't drawn. Because it has a positive charge, it has these 3 bonds and an empty p orbital, giving it an incomplete octet. What happens in this case, where carbon 3 has a p orbital, is instead of having the 2 pi electrons stuck between carbons 1 and 2, like I showed on the previous page, in this case, the 2 pi electrons are spread or delocalized across all of my carbons, numbers 1, 2, and 3. Because I have 3 carbons involved, I will have 3 p atomic orbitals put in, and I'll get out 3 molecular orbitals. Below, I'm going to draw our 3 molecular orbitals. The lowest energy one is where we have completely constructive overlap of the 3 p orbitals from carbon 1, 2, and 3. Notice that I have phasing match over the whole top of the molecule and over the whole bottom of the molecule from the 2 lobes of my p orbitals. I call this my bonding molecular orbital. Remember that for molecular orbitals, as we go higher in energy, we add nodes, or places where we have sign changes across the molecule. Our middle energy molecular orbital has a node cutting through the middle of the molecule. And it turns out this node cuts right through carbon-2. What this means is that I don't have any lobes on carbon-2. My lobes that look like p orbitals are only on carbons 1 and 3. Notice that in this molecular orbital, an unshaded lobe of carbon-1 is across from a shaded lobe of carbon-3, and the same on the bottom half of the molecule. This means that there isn't bonding occurring because the shading needs to match for a bond to be present. We call this the non-bonding molecular orbital. Going even higher in energy gets us to a molecular orbital where we have two nodes. These distribute themselves evenly in our molecule, so I have a node between carbons 1 and 2, and a node between carbons 2 and 3. Because of this, I have multiple sign changes, or shading changes, as I cross my molecule. So notice on the top, I go from unshaded lobe to shaded, back to unshaded. When I have these sign changes here as well, there isn't bonding between any of these carbons. I call this highest energy molecular orbital my antibonding molecular orbital. Now let's consider how many electrons we have and where they will reside. Looking at our molecule up above, I have 2 pi electrons filling the pi bond between carbons 1 and 2, and carbon 3 has an empty p orbital, so it isn't contributing any electrons. I only have 2 pi electrons total, and they're going to fill my lowest energy orbital, known as my bonding molecular orbital. This leaves my non-bonding and anti-bonding molecular orbitals unfilled. Because my original molecule has a positive charge, you can think about this as being an electron-deficient compound, and we can wonder about where is the electron deficiency present. Essentially, where is the positive charge? You can think about the positive charge as being present in the non-bonding molecular orbital. This is the orbital that would get filled if we had more electrons, but we don't have any, so it's empty. We can look at this molecular orbital to judge where the positive charge is present. Because this molecular orbital only has lobes on carbons 1 and 3, this means that carbons 1 and 3 have the positive charge in this molecule. The way that we draw our resonance structures is going to have to account for the fact that carbons 1 and 3 have positive charge. And in fact, there is a second resonance structure for our original molecule. In this other resonance form, carbon 1 has a positive charge, and the pi bond is present between carbons 2 and 3. The rules that I'll explain in this video are to get you to these correct resonance structures that accurately predict where charges are present in your molecule. Before we begin drawing resonance structures, I want to give you some key terminology. A term that you'll hear come up is resonance contributors. Each resonance contributor is one of a set of resonance structures, and our resonance structures will only differ in their placement of electrons in the molecule, never the placement of the atoms. We'll draw what's known as a resonance hybrid, that is, a combination of all of our resonance contributors. Make sure to always draw resonance structures in brackets with resonance arrows between them. The resonance arrow is a double-headed arrow. So looking at our same molecule from the previous page, I drew 2 different resonance structures. These could be called resonance contributors. I put brackets around the whole set of resonance contributors, and I put a double-headed arrow, known as a resonance arrow, between the structures. Here's an example of how I would draw my resonance hybrid for this molecule. First, let's deal with the bonds and then we'll deal with the charges. Alright, so looking between carbons 1 and 2, in each case, notice that I have a double bond in one resonance structure and a single bond in the other resonance structure. You could think about, on average, this is a 1.5 bond, sort of the average between 1 and 2. I would draw this in my resonance hybrid as a solid line for one bond, and then a dotted line for a half bond. Then I have the same thing between carbons 2 and 3. The way I draw charges in my resonance hybrid is anywhere that's charged in my resonance contributors has that same charge, but it's a partial charge in the resonance hybrid. So notice that carbons 1 and 3 are charged in my resonance contributors. In my resonance hybrid, carbons 1 and 3 will each have a partial positive charge instead. We're trying to come up with a way of essentially averaging all of our resonance contributors together into a single structure. So to summarize, in our resonance hybrid, we use partial bonds and partial charges to show how our electrons are delocalized or spread throughout our molecule. We're going to consider resonance to be the spreading of electrons over more than 2 p orbitals in a molecule. This spreading of electron density is known as delocalization. Having these electrons delocalized in a molecule is always going to stabilize that molecule. Therefore, resonance is a stabilizing effect. I'm going to introduce a new tool that we'll use for resonance and for the rest of the semester for keeping track of electrons. This is going to be called curved arrows. The arrow can be considered to have both a head and a tail. You place the tail of the arrow where the electrons are coming from originally, and you'll always place the head of the arrow where the V is put, where the electrons are going to. We're going to have 5 patterns to look out for resonance, and the first one of these is when you have a pi bond next to an empty p orbital. This is the case in the molecule we saw before, where we have a positively charged carbon directly adjacent to a pi bond. This particular molecule is known as an allylic carbocation, or the allylic cation. Carbocation refers to a carbon with a positive charge. To show how electrons would flow from this molecule to get us to our other resonance contributor, I'm going to draw one curved arrow. Be very deliberate here. The curved arrow has to go from the middle of the pi bond to the middle of the carbon-carbon bond. This curved arrow means that our electrons move to between the middle and the right carbon, and this takes away the electrons from the left carbon, leaving it with a positive charge. Instead of these 2 individual resonance contributors, I could draw a resonance hybrid where I have dotted lines going across all 3 carbons, and I have partial positive charges on the carbons on the left and the right. You can think about the one curved arrow that I drew as moving the location of the pi bond. For resonance, you want to be on the lookout for patterns rather than exact molecules that you've seen before. So below, I've shown a different molecule where we have the same resonance pattern, but instead of a carbon with a positive charge, I have a boron with 3 bonds. Because boron has 3 valence electrons, when it's neutral, it has 3 bonds, an empty p orbital, and an incomplete octet. So in this molecule as well, I I have a carbon-carbon pi bond adjacent to an empty p orbital, now on boron. I would draw my resonance arrow with the tail in the middle of my pi bond and the arrow head pointing at the middle of the carbon-boron bond. Once I move this pi bond, I now have a boron with 4 bonds and a negative formal charge, and I've taken away the 4th bond from my carbon on the left. This carbon just has 3 bonds now. There are 2 hydrogens that aren't shown, so now it has an incomplete octet and a +1 formal charge. To draw my resonance hybrid in this case, I would have a dotted line running from carbon to boron. This gives my averaging of my 2 resonance contributors and their pi bond placements, and my partial charges are going to reflect the charges in the resonance contributor on the right. So where I have a full +1 formal charge in a resonance contributor, I'll have a partial positive charge in my resonance hybrid, and the same for my negative charge. The second resonance pattern is when you have an atom with a lone pair next to an atom that has an empty p orbital. In this example, my atom with a lone pair is my oxygen, and my atom with the empty p orbital is this positively charged carbon. I would use one curved arrow to get to my other resonance structure. I draw this arrow with its tail at the oxygen lone pair and its head at the middle of the carbon-oxygen bond. What this curved arrow means is essentially take an oxygen lone pair and make a pi bond out of it. And this gets me to my other resonance contributor. In this, I have a new carbon-oxygen pi bond, and my oxygen now has 3 bonds and a positive charge. So to reiterate, our curved arrow here is converting a lone pair into a pi bond. Because in one structure I have a carbon-oxygen single bond, and in the other structure I have a carbon-oxygen double bond. In my resonance hybrid, I have 1.5 bonds with 1 solid line and 1 dotted line. The carbon and the oxygen in the middle of the molecule both have partial positive charges. Notice that in my resonance hybrid, as well as in the resonance contributor on the right, my oxygen is sp2 hybridized. Essentially, oxygen, rather than adopting an sp3 hybridization as predicted, will be sp2 hybridized instead, in order to participate in resonance. I'll talk more about this toward the end of the video. We can also have the same pattern where we swap out our atoms. For example, let's consider this molecule where I have a nitrogen with a lone pair next to a boron with an incomplete octet, and therefore having an empty p orbital. I'd draw my curved arrow with the tail from the nitrogen lone pair and the head at the middle of the nitrogen-boron bond. In my other resonance form, I now have a nitrogen-boron double bond. Because the nitrogen has 4 bonds here, it has a positive charge, and because boron has 4 bonds, it has a negative charge. These are full formal charges. In the resonance hybrid, I would have my dotted line between nitrogen and boron, and I would have partial positive and partial negative charges. My third pattern is if I have a lone pair adjacent to a pi bond. In this example, I have a carbon-carbon pi bond that is next to an oxygen with 2 lone pairs. Watch carefully how I would draw my curved arrows here for this resonance pattern. For this resonance pattern, I need 2 curved arrows. The first one takes a lone pair and makes a new pi bond. And then the second one goes from the middle of the pi bond to the atom on the end of the chain. We could call this our terminal atom, in this case a carbon. After these curved arrows, I get to a resonance contributor where I have a new oxygen-carbon pi bond, and I have a new carbon lone pair on the end of the molecule. This carbon has a negative charge, and the oxygen with 3 bonds has a positive charge. The resonance hybrid would have dotted lines running from oxygen to carbon to the other carbon, and I have partial positive on oxygen, partial negative on carbon. Just the terminal carbon, though. For this pattern in particular, you have to be very careful not to break the octet rule. Common ways to break the octet rule would be bringing down the lone pair to form a pi bond without breaking the other pi bond, or accidentally bringing the pi bond to the middle carbon instead of the end one. We can get situations where we have more than 2 resonance contributors if the resonance can extend along a long chain. So let's look at this molecule where we have a lone pair, now on a carbon instead of an oxygen, and that lone pair is adjacent to one pi bond, and then there's another pi bond adjacent to the middle pi bond. I'm going to start with my lone pair adjacent to a pi bond resonance pattern. Now I have a resonance contributor where I have a carbon lone pair that is adjacent to another pi bond, further toward the right of the molecule. I can draw my resonance pattern 3 again. I bring down my lone pair to form a new pi bond, and move my pi bond to the terminal carbon to get a new lone pair and a negative charge. Looking at my resonance contributors, any carbon with a negative charge in one resonance contributor will have a partial negative in the resonance hybrid. So I would have 3 partial negatives here. Our fourth resonance pattern is if you have a polar pi bond. This is an example of acetone, a simple ketone. My carbon-oxygen pi bond is polar, with oxygen being more electronegative than carbon. My resonance arrow here would go from the middle of the polar pi bond up to the more electronegative atom. This one curved arrow takes the 2 electrons from the pi bond and makes a new lone pair on the more electronegative atom. In the other resonance contributor, now that it's lost the pi bond, the carbon has 3 bonds and an incomplete octet, giving it a positive formal charge, and oxygen now has 3 lone pairs and 1 bond, giving it a negative formal charge. In my resonance hybrid, I would have a solid line and then a dotted line between carbon and oxygen. The carbon of the polar pi bond would have a partial positive charge, and oxygen would have partial negative. Sometimes you'll need to show a combination of different resonance patterns, and my hint is to show one at a time. So let's consider a molecule where I have a ketone that is adjacent to a carbon-carbon pi bond. First, I'm going to show the pattern for the polar pi bond resonance pattern. After I move this pi bond up to oxygen, my carbon is positively charged and my oxygen is negatively charged. I've now unlocked a new resonance pattern, which is an atom, in this case a carbon with an empty p orbital, adjacent to a pi bond. I can draw a second resonance pattern by moving my pi bond to make a new pi bond. This gets me to a third resonance structure, where oxygen still has 3 lone pairs and a negative charge, but my carbon-carbon pi bond has moved, and now my carbon on the end of the molecule has the positive charge. In my resonance hybrid, I would have dotted lines running from oxygen to carbon to carbon to carbon. I would have two sites, both carbons with partial positive charge, and I would have oxygen with partial negative. To recap, the two resonance patterns I used in this case were first the polar pi bond resonance, and then the pi bond adjacent to an empty p orbital. My final resonance pattern, and luckily I think this one is the easiest to spot, is when you have a system of a ring of atoms with alternating single and double bonds. You could call this having contiguous pi bonds in a ring. Here's an example of a 6-carbon molecule known as benzene. For this resonance pattern, what you're going to do is move all of your pi bonds simultaneously. In this case, because I had 3 pi bonds, I had 3 curved arrows. Each arrow goes from the middle of a pi bond to the middle of an adjacent single bond. This has the effect of moving all of the pi bonds at the same time. My resonance hybrid in this case doesn't have any partial charges, but I have a ring of dotted lines. I want to end by talking about lone pairs and hybridization. Because if a lone pair participates in resonance, that can change an atom's hybridization. We'll use the term localized lone pair to describe one that doesn't participate in resonance. For example, let's look at the following amine. I have a nitrogen bound to 3 different carbons, and that nitrogen has a lone pair. This molecule doesn't have any of the resonance patterns we discussed. Because of this, we follow our usual hybridization rules. The nitrogen has 4 electron groups around it, therefore it is sp3 hybridized. Here I've redrawn my molecule to emphasize its 3-dimensional shape, which is trigonal pyramidal. And because nitrogen is sp3 hybridized, the lone pair is in an sp3 hybrid orbital. We'll use the term delocalized to describe lone pairs that participate in resonance. And the super important rule here is that a lone pair needs to be in an unhybridized p orbital in order to participate in resonance. So let's consider the following molecule, where we have a nitrogen with 2 hydrogens, a lone pair, and the nitrogen is adjacent to a pi bond. This molecule has our resonance pattern of lone pair adjacent to pi bond. To get my other resonance contributor, I would draw 2 curved arrows. I bring my nitrogen lone pair down to form a nitrogen-carbon pi bond, and I break my carbon-carbon pi bond and bring those electrons to my terminal carbon. The rule is that this nitrogen lone pair, in order to engage in resonance in this way, it needs to be in an unhybridized p orbital. The reason for this is it needs to be in a p orbital so that the p orbital from nitrogen can overlap with the p orbitals from the 2 carbons engaging in the pi bond. What this means is that even though nitrogen has 4 electron groups around it, the nitrogen puts its lone pair in a p orbital and becomes sp2 hybridized and trigonal planar in order to engage in resonance, simply because resonance is such a stabilizing factor for a molecule. Alright, so we've covered a lot of ground today. I talked about molecular orbitals for pi bonds, either for localized or delocalized pi systems. I showed you how to use curved arrows to show the flow of electrons between resonance contributors, and I showed you 5 patterns to look out for drawing resonance structures. And last, I just introduced this hybridization issue for resonance. That's it for this video. I will see you in class.